Okay, let's finish the other example. There's another subtlety that where how about the F has the poles of F have the same location as the cotangent or the uh, whatever the function is. So we need to deal with that one. So this is 11.9.2. Now the series is again is start from one instead of minus infinity n times n plus one. Right. Now this is slightly more complicated. Then what you need to do is to change that, like this. You like to change the variable that cover the negative n. So I usually just do n to minus m or something like that. But you use minus m, this is not exactly the same one. It's become minus m plus one. Is there's a negative sign. And what we could do is this minus n equals to minus m minus one. That probably will do it, right? So I usually need two steps. I usually cannot do it in a single step. So n is minus m minus one. N plus one is minus n, right? And this is n is one means n is if n is one, then m is minus two. Move one to the other side and m to the other side, and m is minus two. And obviously n is minus infinity, that m is minus infinity. Okay, and now you can cancel all the negative sign. And this is exactly of the same form. Then you can call your m equals to n, 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 n. So exactly the same. Okay, now you just sum, so s or 2s is sum over n is minus infinity to infinity, 1 of n plus 1, except that it skip the point minus 1 and 0, right? Because this is summing over mega infinity to minus 2. This is from 1 to infinity. So you skip the 2, 0, and minus 1. But we don't, now this time we don't want to add and subtract that because the function is singular at those locations. So we can just say that n is not equals to 0, 1 minus 1 and 0. I think your text will use a pine to indicate that, but then you can also explicitly say that it's not equals to minus 1 and 0. Right? So that is our series. Now, this is different from the, the derivation, but then we can deal with that by when we evaluate that pole, we separate that two poles. So this is my f. F I only have two poles now, 0 and minus 1. So all the poles are on the real axis, or the real integer, or the integer vector, right? So, so this sum is all the integer except minus 1 and 0, except this two, you sum over all this, right? Which means when we derive the formula, we need to treat these two poles separately because these poles are the poles of cotangent and also the poles of F. So that most likely those are second order pole, right? So the F, this is your F, right? So F, Z is 1 over Z, z plus 1, right? And the function we want to calculate is now pi cotangent pi z times f, which is divided by z and z plus 1, right? Now all the other poles of cotangent will give you this series. You already know that, or the negative of that one. So, so what the rest is the residue at 0 and -1 at this occasion, but they are second order pole because they are both cotangent and this denominator the poles are due to this cotangent and the denominator is 0, right? So those are second order poles. So, so what is you're saying this integral is equals to, instead of the formula, you change that to negative of the residue of 0 and 1. Okay, of this one, and this would be this series without this two terms, because when we evaluate the big circle, evaluate all residue, this is just including all these other poles, and leave these two poles separately because these two poles are the same at the same location where f is singular. Okay, so we treat that separately. It's okay. So that how you treat it, the situation where the poles of f is at the same location as the function. In this case, the cotangent. It's okay. So so there are two second order poles, and the residue is, well, let's see if we can drop that. That's a little bit. I mean, second order pole, you remember the formula. Right? So this is the residue that you want to calculate. So z equals 0 means you multiply by c squared and then take the derivative, right? So equals, so there are two terms. One is limit of z equals to, that's negative sign to this one. Z equals to 0 and d dz of multiply c squared, so z, that's a pi. So that's the pole at c equals 0. And then the second one is c goes to -1. Right. And then you multiply c plus 1 square, so cancel one of these. C plus 1 cotangent of pi c divided by this. Derivative, quick of that, dbc. Okay. Well, that shouldn't be too hard, right? Yeah, do it one at a time. Some space here. All right, for this one, then we take the derivatives of uh, cotangent is cosine divided by sine, right? I take the derivative of cotangent. Yeah, I forgot. Is it right? I usually need to use change it to sine and cosine. So this is minus pi. Remember that we'll take the limit. Remember later on we need to take the limit. Cosine z plus 1 z. The second order poles become much more complicated because we need to take the derivative. So all the point that are singular is at uh, when sine pi z is 0, when the sine term is 0, right? Uh, and to the other terms are fine. So we'll just consider this the first term. So you take the derivative of cosine pi becomes sine pi. So there are four terms, four vectors you need to take the derivative, right? And so you have you take the z, it becomes cosine pi z equals 1. The first one, and then the second one is z sine pi z, which cancel with the sine pi z, and you actually negative because negative time because you have a pi taking the, and then sine pi z and cancel with this one and divided by z plus 1. This one actually turns out to be 0 because later on we need to set z equals 0, and then the other two are z cosine pi z plus 1 square, and then sine pi z. And the final one is minus z plus 1 sine square pi z, and the other is cosine square pi z. And that's the pi. Right? And take the limit. So there's a limit of z equals to 0. Well, now the taking limit is 1. Now this one is 0. Now this one, sine pi, the limit is pi z, right? C and C cancel, and cosine pi 0 is 1, and this is 1. So this is 1 over pi, right? 1 over pi. Now for the other one, it looks to be singular, but you need to combine the two because combine the two first, right? All the c plus 1 are just changed to 1 because they are fine, right? And now the rest you combine the two, so your cosine pi z, and divided by sine pi z, and then this is 1 minus pi cosine z over sine. And you take the limit of z goes to 0. So this is singular, but then what about this one? So this is when z equals 0. This is close to pi z. Pi z, this is 1. So this is pi z. Well, you suppose it should get pi z can cancel with that, right? And did I do the derivative incorrectly? Oh, when I combine this, I forgot the z. I forgot the z. Yeah, that's why I'm getting in trouble. Z pi cosine pi divided by sine pi. I already take the limits equal to 0. It's just this one, right? Now that more likely because now you can take the limit that because it changed this when small z is pi z, right? You cancel with the pi z cosine pi z. So 1 - 1. So there's this 0 in the numerator and 0 in the denominator that make it possible to have a finite limit. So we need to do it one more step. Cosine pi z, sine z, therefore 1 and minus pi z. And now this becomes user cosine. Cosine is 1 minus pi squared z squared over 2, right? And then sine is pi z minus z cubed plus z. Right? Let's see if we can get something finite out. So cancel the pi z, and then this is square. And then use the binomial theorem to fit that. Let's become cosine pi z. Did I run out of time? Oh, almost. Pi z. Unfortunately, we have the last section that we haven't been able to do. So 1 minus and then this is 1 plus pi squared z squared over 6. Okay, cancel with the 1. So you all have the second order terms in c squared. And then this is pi z. So looks like for this term, actually, these two terms actually combine to 0. Just combine to 0. So all is left is minus 1 over pi and minus, so this is pi. Oh, yeah, and 1 is, the pi cancel with pi is 1. Is it 1? Is the textbook say is 1? Yeah, you don't know. Oh, you can solve it the other way?
No, we can solve it 1 by n minus 1 by n plus 1 using just basic arithmetic, and everything will get cancelled, and at the end it will be just 1 minus 1.
Okay, so you're better at visualizing this. I cannot do that. So, I'm just looking at the textbook now. What the textbook says minus 1. The residue at each pole is minus 1. Why did you get the minus? It's minus. Oh yeah, the residue is minus 1. Yeah, I include this minus sign here. So this is minus sign from the formula. Formula is minus. The residue is minus 1. Include that as 1. Okay, so I did it correctly. So for one thing, and the other thing is just you do the same structure with the others. Should be actually the same because you have the two terms are pretty similar. Okay, so that's how you do it. And I'm running out of time, so I mean there's more than one way. I think your textbook suggests instead of using this second order formula, you just expand that. Let's start with expansion, take expansion of the function, cotangent function, and that might be slightly easier.